3.1, challenge activity 3.14, looking at linear regression equation for line of best fit. This is where it's talking about, so before we were talking about the relationship, we had linear, nonlinear, and within linear we had positive and negative correlation. So now we're just talking about looking at that actual regression equation and how to utilize it or interpret it. The scatter plot shows a relationship between the amount of rain received in a year, that's your X down here, and the average diameter of a fruit in a particular orchard that year. That's your Y, your response variable. Is a linear model appropriate for this data? I mean, it does show an overall linear pattern, and I think it would be reasonable to go ahead and say yes. So let's check our answer. If it lets me check. Yes, because look, it shows an overall increase. Does it have a huge amount of correlation? Maybe not. Maybe the correlation won't be strong, but there does seem to be some at least moderate correlation. Let's look at the next section. The scatter plot shows the relationship between the mass of a tree and the total mass of the vegetation within 100 square meters of the tree. You see here, mass in tree is your X, so as a tree gets bigger, what they're saying is the mass of vegetation within 100 square meters of it goes down. So they're saying that there might be less vegetation around a larger tree. It does, again, show an overall linear pattern. You see a lot more dispersion here on the higher end, but still, it does show overall with some outliers that there might be a linear pattern with a negative correlation. Let's go ahead and say yes. And check. Yep, that's true because it does show a decreasing pattern. The scatter plot shows a relationship between the distance from a 5 kilogram mass of plutonium-239 and the number of emitted alpha particles detected per second in a 1 square meter area. This is looking at radiation. So here we have distance from that plutonium, that thing, and then we have the number of alpha particles here. Obviously, these are gigantically hard numbers to read. One thing that I noticed right off the bat is that we have a very curved pattern here. We do see a pattern. This is definitely a non-linear pattern due to that curve. All right, so is a linear model appropriate? No. All right, that's expected, so correct. Let's go to the next one. A scatter plot shows the relationship between the amount of rain received in a year and the average diameter of a fruit in a particular orchard that year. So here again we have rain and then diameter of the fruit, and we do see, like we saw earlier, that as the X increases, the Y increases. So here we're looking for the slope. Remember, slope, let's make this a little smaller. We have slope equals rise over run, and I posted about this last week, but just to make sure it's clear. So what we're looking at here is like y2 minus that's y1 over x2 minus x1. The idea is that you want to pick any 2 points on this line, not the data points, on the line. You want to take whichever one's on this farther down the x-axis and subtract off the points that are farther down on this end of the x-axis. The reason for that is if you mix those up, you might show a negative correlation when it should be positive and vice versa. So you want to make sure you pick one over here. The idea here is that you just want to find 2 points that intersect the grid lines to make it easy. You can use other points. It's just to make your life a little easier. So here we see one set of points. I'm going to write the coordinates right here. We have, what is that, 15 and 10. So that's our X is 15 and our Y is 10. And then our point down here, I'm going to go ahead and just use the intersect because I know X equals 0 and it intersects at a nice little grid line. So we're going to say 0 and 5 for our next point. So when we come over here to put this into our slope formula, this is our, remember this is our point 2 and this is our point 1. So we're going to start with y2 minus y1 over x2, which is 15 minus x1. So that gives us 5 over 15, which is about 0.33. Remember, that's 1/3, which is about 0.33. And if you don't remember that, you can put it into your calculator. So we're going to go ahead and put it now. I want to point out something, and this is an issue I've reported. For anyone that came across this, let me know, and we'll address it again. You do need to type in 3 decimal points here, 333. I have reported this to Zybooks. They need to be specific in the number of decimals you need. So let me know if you had that issue, and we'll go from there. All right, the intercept, as we already said, is at 0 and 5. So they just want you to put in that 5. We already found that when we were looking at our 2 points. So now let's put that all together in our regression equation. So the intercept is going to be 5, and you can tell which one goes where because remember your slope is multiplied by your x, and your intercept is just added or subtracted depending if it's positive or negative. So here we're going to put 0.333 times x, and then we have plus 5. So let's go ahead and check our answer. Expected, exactly. And it shows here, they even chose 2 different points. They chose 10, 15, and 9, 12. So again, you can pick any 2 points on the line. It's just anywhere, it's easy for you to figure out what points you're looking at. So on to part 5 of this question. The scatter plot shows a relationship between the mass of a tree and the total mass of the vegetation within the 100 square meters around the tree. Well, here's the negative relationship. Excuse me. So as the tree gets bigger, we expect to see less vegetation around that tree. So just like we did before, we need to find 2 points. So I'm going to go ahead and start with the second point first, like our x2 and y2. So I'm going to look over here. It looks like there's a good, well, let's go with this one because I can see it. The other one has a data point. I can't exactly see it. Here I know there's an intersection right here. So it looks at x is 2,000. And let's come across to our y, and that's 30, right? 30. Let's get our point 1. So again, you can either use like an intersection here, or you can just use the intercept. Me personally, I think the intercept's the easiest, and then you answer the next question too. And it's easy because you already know your x is equal to 0. That's an easy one. So here it looks like 50, right? We have 5, 10, 15, 20. Right, there you go. Yep, that's going to be 50. All right. So let's come over here to our little worksheet, I guess. We have rise over run again. Remember that's y2 minus y1 over x2 minus x1. So that equals, remember this is our y2 and y1. So we have 30 minus 50. And then this is our x2, 2,000 minus 0, because it's our x1. Remember, we want to get a negative number here. This is a negative slope. X is increasing as Y is decreasing. So right here, we see that we're going to get our negative number, and that's good. That means we've set them up the right way. So when we subtract this, we get negative 20 over 2,000, which is the same thing as negative 1 over 1,000. Excuse me, 100. There we go. 100. And when we convert that to a decimal, we get negative 0.01. All right, so let's go ahead and put that over here as our slope, negative 0.01. And then our intercept we already found is at 50. So we have 50. So we're going to put our intercept in here. Remember, there's nothing it's multiplying by, it's just being added. And here we're going to put in our slope because we're multiplying it by x. We have negative 0.01. I'm going to check our answer. Expected. There we go. We have that negative 0.01, 50, 51. The idea is that they even chose 2 different data points just like in the last one. So it's just important to make sure you have them in the right order and pick those lines. If you have any questions about that, let me know. Again, that's the negative regression example. Let's go to the next section. The scatter plot shows a relationship between the number of coffee drinks sold and the total expenses of a coffee shop. The idea here is as we increase the number of coffee drinks sold, our expenses go up, which makes sense. I mean, that's not talking about your profit, your expenses, because you have to buy more cups, more supplies, more coffee, maybe even hire more employees. So there's a lot of stuff connected to the additional sales. So here we're given the regression equation, y hat equals 500 plus 2.5x. What is the interpretation of the slope? Remember, the slope tells us for every unit increase of x, this is how much y increases. So let's look at our options. As coffee drinks sold per dollar spent by the shop, remember we're using x to predict y, so our slope is going to tell us something about our y variable. Definitely doesn't tell us our price per coffee drink. Here it says total expense to the shop per coffee drink sold. Well, like right here, every unit increase is 1 coffee drink sold. So that makes sense. It's total expense to the shop, total increase expense to the shop per coffee drink sold. And then what is the interpretation of the intercept? Remember, the intercept tells us tells us what y is when x is equal to 0. So in this case, what happens when there's 0 coffee drinks sold? Does the business just stop running? Is it zero? No, they still have operating expenses. Even if they don't sell any coffee drinks, they still have to pay for employees, electricity, all that. So it's not that it's no practical interpretation, because it does tell us some kind of baseline. It says the number of coffee drinks sold even if the shop spends nothing. Well, that makes no sense, because we know right now the number of coffee drinks sold at the intercept is 0. So what the shop spends even if no coffee drinks are sold. Well, there you go. So if the coffee shop sells 0 coffee drinks, that intercept is still telling us what their operating costs are that day. All right, let's check. That's it. All right, let's look. All right, the last one. The scatter plot shows the relationship between the time spent to complete the first project and the number of projects attempted in a week. So, as we increase the number of minutes spent on the first project, we expect that we might get less done that week. That makes sense. So we do see a negative correlation here. So it gives us the regression equation, y hat equals 23 minus 0.067x. The interpretation of the slope. Remember, the slope's going to tell us that for every increase in the x variable, what do we expect? In this case, it's a decrease in the y variable. So we're looking for the expected amount or change in the y variable. It tells you the average amount of time spent on a project. That's not it. The expected amount of time spent on the first project given the number of projects attempted in a week. That would only be the case if the x and y were reversed. That doesn't make any sense here. And then it says the expected number of projects attempted in a week given the amount of time spent on the first project. Well, that makes much more sense. So it's telling us that as this decreases, that's what we would expect based on that time from the first project. What is the interpretation of the intercept? The intercept, again, sorry, just to reiterate, the slope even gives us a little bit more than just that expected number. It actually talks more about the change too. So for every increase in x unit, so for every additional minute spent on that first project, this is the amount of fewer projects we expect, that decrease, right? So like if we go from 25 to 26 minutes on that first project, we expect 0.067 less projects to get done that week. All right, what is the interpretation of the intercept? That's when the x is equal to 0. So remember we talked about this in a couple other things where sometimes it doesn't make sense to interpret the intercept. In some examples like this one, would we ever spend 0 minutes on the first project? If we're spending 0 minutes on the first project, that's definitely means we have no projects, right? So in this case, it really doesn't make sense to interpret the intercept. So we're not even going to go dig deeper into the other options. There's no practical interpretation. So let's check. That's expected. All right, that is 3.1.4, the linear regression equation for line of best fit. If you have any questions about this or anything else in 3.1, let me know.